Good day, this is the Professor, CBFD PhD, and today's Friday, May 26, 2023. It is 2:57 and 14 seconds, a.m. Eastern Daylight Time, and today's research, laser pulses. So let's jump to it here. Laser pulses with record-breaking intensity, high-intensity pulses, allow astrophysical phenomena to be studied in the laboratory. Date May 6, 2021. Source: The Optical Society. Researchers have demonstrated a record high laser pulse intensity of over 10 to the exponent 23 waves over centimeter squared using a beta 1 laser. It took more than a decade to reach this laser intensity. These ultra-high intensity light pulses will enable exploration of complex interactions between light and matter in ways not possible before. The powerful laser can be used to examine phenomena believed to be responsible for high-power cosmic rays, which have energies of more than a quadrillion, 10 to the power of 15, electron volts. Although scientists know that these rays originate from somewhere outside our solar system, how they are made and what is forming them has been a long-standing mystery. As this high-intensity laser will allow us to examine astrophysical phenomena such as electron-photon and photon-photon scattering in the laboratory, we can use it to experimentally test and access theoretical ideas, some of which were first proposed almost a century ago. As studying laser-matter interactions requires a tightly focused laser beam, and the researchers were able to focus the laser pulses to a spot size of just over 1 micron, less than 1/15th the diameter of a human hair. The new record-breaking laser intensity is comparable to focusing all the light reaching Earth from the Sun to a spot of 10 microns. And this high-intensity laser will let us tackle new and challenging science, especially strong-field quantum, electrodynamics, which has been mainly dealt with by theoreticians. In addition to helping us better understand astrophysical phenomena, it can also provide the information necessary to develop new sources for a type of radiation treatment that uses high-energy protons to treat cancer. The new accomplishment extends previous work in which the researchers demonstrated a femtosecond laser system based on Ti sapphire that produces 4 beta 1 pulses with durations of less than 20 femtoseconds, while focused to a 1 micrometer spot. And this laser, which was reported in 2017, produced a power roughly 1,000 times larger than all the electrical power on Earth in a laser pulse that only lasts 20 quadrillionths of a second. As to produce high-intensity laser pulses on target, the generated optical pulses must be focused extremely tightly. In this new work, the researchers applied an adaptive optics system to precisely compensate optical distortions. As this system involves deformable mirrors, which have a controllable reflective surface, shape, to precisely correct distortions in the laser and generate a beam with a very controlled wavefront. They then use a large off-axis parabolic mirror to achieve an extremely tight focus. The process requires delicate handling of the focusing optical system. The years of experience gained while developing ultra-high power lasers allowed them to accomplish the formidable task of focusing the beta 1 laser with a beam size of 28 centimeters to a micrometer spot to accomplish a laser intensity exceeding 10 to the power 23 weight centimeters squared. The researchers are using these high-intensity pulses to produce electrons with an energy of over 1 giga-electron volts, 10 to the power of 9 electron volts, and to work in a nonlinear regime in which one electron collides with several hundred laser photons at once. And this process is a type of strong field quantum electrodynamics called nonlinear Compton scattering, which is thought to contribute to the generation of extremely energetic cosmic rays. They will also use the radiation pressure created by the ultra-high intensity laser to accelerate protons. Understanding how this process occurs can help develop a new laser-based proton source for cancer treatments. And sources used in today's radiation treatments are generated using an accelerator that requires a huge radiation shield. A laser-driven proton source is expected to reduce the system cost, making the proton oncology machine less costly and thus more widely accessible to patients. The researchers continue to develop new ideas for enhancing the laser intensity even more without significantly increasing the size of the laser system. One way to accomplish this would be to figure out a new way to reduce the laser pulse duration. As lasers with peak power ranging from 1 to 10 petawatt are now in operation in several facilities, reaching 100 petawatt are being planned. There is no doubt that high-intensity physics will progress tremendously in the near future. And this is a professor of microbiology, bioinformatics, pathophysiology, and leader of research. This video was created for educational purposes only. Hope you enjoyed listening. Until next time, have a great day.